And basically, just a review of what Newman projections really are is kind of viewing down the length of a bond. It's as if you were looking at a molecule like that, okay? So the bond would be the length of the pencil, and then there'd be a carbon on each side of it. And it's as if you were looking straight down like that, where you wouldn't really be able to see the bond nor the carbon behind it. So that's what it's kind of trying to represent. So the dot in the middle here would be the carbon in front, okay? And the circle in the back would represent the carbon in the back, okay? Anything coming off of the carbon in this pink color would be coming off of the front carbon, and anything coming off of the blue would be coming off that back carbon. Okay, so I'm going to demonstrate, I'm going to draw this out. The way I always translate Newman projections to the nomenclature or the line structure is first by drawing it really ugly, so I can just make sure I have everything down, and then I redraw it to get a clean copy I can interpret. So I'm going to start here with my pink carbon. I have a propyl group coming off of there, so that means 3 carbons, 1, 2, 3, and then I have a chlorine, and I also have a methyl group. Okay, and in black or gray here, I'm going to draw the bond that we really can't see, but it's right there. It's between the pink and blue carbons. Okay, so here is going to be my blue carbon, and it's going to have a hydrogen coming off of it, another hydrogen, and an ethyl group. Okay, so I'm going to redraw this molecule. I'm not going to include my hydrogens because we don't really need that when we're naming. So now I've just redrawn everything a little bit neater so I can interpret it. And I'm going to do everything like we did before, find the longest chain, and the one with the lowest numbering scheme. Here we have a symmetric molecule, so no matter which direction we go in, we'll still get the same answer. So we have a methyl group here and a chloro group. When we put this all together, our base chain will be 1, 2, 3, 4, 5, 6, 7. So 1 to 7, and this will be 2, 3, 4. Okay, and we're going to alphabetize those. So we'll see 4 chloro, 4 methyl, and this is heptane. Okay. Why does the propyl look different? Did you draw a butyl instead of chloro? 1, 2, 3. No, I don't think I did. So this still has 3 carbons, just as this did. Okay, so nothing changed there. If that's what you're referring to, this is also an ethyl, which didn't change from here. So yeah. Okay. Any more questions on this? Why do we not draw the hydrogen in the back carbon? I didn't. I mean, for sure it's there, but it doesn't help me name it, and so I just didn't draw it again. When we do line structure, we don't really have to draw any of our hydrogens. We assume it's there. I just drew it in the first one, so I can easily translate between Newman projection and line drawing. Okay. Any questions about Newman projections? Wouldn't we number it the opposite to the closest subset? Substituent. Opposite. I'm not sure what you mean there. So this molecule is symmetric, so no matter which direction we go in, it doesn't really, okay. All right. So now we're going to attack this. I know it looks very scary. Okay. But it's not too bad, you guys. I've seen more awful ones. So typically you're going to get something like this. Oh, I'm sorry. We can go back for sure. typically you're going to get, for RNS, you're going to get one of those fat giant molecules on your exam, like you did on your quiz, is what I believe you're probably going to see. So you kind of have to get used to breaking them down and handling really big molecules by focusing on just components of them at a time. So, and again, by the way, I will be sending you guys all the slides, so don't panic. For these questions, would you suggest drawing out the section with the stereocenters? Yeah, the thing is, it will take forever sometimes. If you really need to, for example, like if you're not getting the question right, or you're just really unsure, I would draw them. I would redraw the portion. I can't remember if I did that or not. I probably did, because it's really hard to do in your head. I probably did do that. So if it helps you, yes. Okay, so for number 1, we're going to start here. Well, first I should actually explain, how do we even start to label RNS? And to that, I would say priority is based on what quality of an atom. What quality of an atom is priority based on? Only one thing, not the atomic weight, atomic number, okay? So let's say here that this portion here, okay, has a much bigger weight, okay, than this portion, or even has 2 oxygens as opposed to 1. So wouldn't this be higher priority? No, because this is a race, okay? Treat this like a race to the highest priority atom. Okay, so how do we rank priority? Again, we just said atomic number. And so you'll see things like sulfur, which is higher than oxygen, which is higher than nitrogen, which is higher than carbon, higher than hydrogen. Okay, and so this is a race here. So it takes a few times to branch out to finally get to those oxygens, whereas over here, we just got it in one step. Okay, we reached that high priority group. Okay. Another thing to consider here, we have a methyl group, okay? And I'm going to tell you right now, that is our lowest priority group, okay? I want to highlight hydrogen doesn't have to be lowest priority group. It could be other things, like this methyl in this case, which is lowest priority compared to everything else here. Okay, it does not have to be hydrogen. What it has to do, though, is be in the back. Okay, we want our lowest priority group to always be in the back. It doesn't have to be a hydrogen. It has to be the lowest priority group in the back. How do we know if it's in the back? It's dashed. Why is the one you starred number 2? Oh, blue. So we're going to do 3 problems, okay? We're going to do problem number 1, which I'm going to do in red, problem number 2 in blue, and then problem number 3 in green, okay? So these are 3 separate problems, okay? Not priority, yeah. Can you go over how to go over a group? Because sometimes I get confused trying to figure out which groups to go out of. Yes, we'll walk through these examples together. So I just want to create a basis for us to go forward. Okay, so I talked about priorities and how this is a race, okay, a race to the highest priority group. And I talked about how hydrogen doesn't need to be the lowest priority group, but we need it to be in the back, okay? So we need lowest priority group. In the back. Okay, and what if it's not in the back? What do we do? We're going to solve our question like normal. And then what? What do we do at the end if our lowest priority group is wedged instead of dashed? If it's in the front instead of in the back, we flip. You could do the thumb trick, which sounds pretty difficult. And maybe it does help you see things in 3D. But simply, we're going to turn an S into an R and an R into an S, okay? What's really happening in space is we're breaking this apart and changing the stereochemistry. And so we get the configuration, the opposite configuration. That's kind of what the thumb rule, I think, is trying to, or the thumb trick is trying to show you, is that we're really changing this molecule stereochemistry to force the lowest priority group in the back. Okay, that's what we do when our lowest priority group is not in the back. Okay. Last thing I want to discuss, double bonds. Okay, double bonds. Double bonds count the atom twice. Okay, it's as if there were two of them. That's how we use double bonds when figuring out R and S configuration here. Okay, so let's start at the beginning. Let's start with our first example. Actually, let me see if I answered a question. What do we do if we have two oxygen groups and where to go from? It is the same thing you would do if there were two carbons. It's the exact same thing. And we're going to cover some examples. Let me see. We do have two oxygens here, so we will cover that. Okay. So we established that our fourth priority group is that methyl group here, CH3 group. In the back, it's solid. And Anissa, yes. Okay, so we also know that our first priority group is going to be this oxygen. Why? Because the only other comparisons here are two carbons, which are not higher priority than oxygen. Okay, but we do have a dilemma because we do have two carbons, which is a pretty common situation. So we are going to need to branch out to see which one reaches higher priority groups first. Okay. And so that must mean we need to branch out, and we're going to branch out in every direction. Okay. And then there's some hydrogens here, but I would not even consider hydrogens for labeling R and S at all. So, all right. Already I've run into a high priority group right here. Okay. And so in one step, I reached a carbon and an oxygen on this carbon. And on the right side carbon right here, I only reached a carbon and hydrogens, but they don't really count. They're pretty sad and don't really help anything. So that means that this one would win priority on the left. Okay, this would win priority, and this would be third priority. Okay, and I'm going to connect these. I'm going to see which direction it's going in. Okay, this is going in kind of a right direction, in a clockwise direction. So we're going to label this R, okay? If it was going left in a counterclockwise position, we would label it S, because S in Latin really stands for sinister, which means left. I thought we have to follow the main ring structure first, and if it stays the same, then we do substituents next. No. So we don't have to follow the main ring. We just follow everything that comes off of the carbon. Yeah. If your ring is symmetrical, then you don't have a stereocenter. If you have something like this, this is not a stereocenter, because if you go this way or if you go this way, you'll get the same thing, okay? Otherwise, you do need to consider the substituents that come off of the ring. Okay. All right, so now we know our priority 1, 2, 3, and 4. Our 4 is in the back. So whatever we get here, which is the R, we keep it, okay? We don't have to switch it. So our answer for this one is R. Yeah, I'm not sure, Matthew. Maybe it was a specific case. Yeah, I'm not too sure. It probably was not the same thing as this one. Can you go back to the benzene with no substituent one. Oh, this is actually not a benzene, but it's a cyclohexane. So yes, this one will not be a stereocenter, because even if you go this way or this way, you're going to get the same group. So you only have 3 groups that are the same here, or that are different, and it's not a stereocenter. What if one meets an oxygen and one meets an OH group? Is the OH group a higher ranking? I would say you're not really ever going to see that, because that's just not enough to. The thing is, let me think of an example. Because that requires another branching event. This is the only case where that situation can happen, because you can't have an O by itself. It needs to be connected to something. So it means you have to have gotten, you have to keep going. And yeah, Matthew, you can email me later and I can answer that question. But 1, 2, 3, yeah. So in that case, this one would actually win higher priority because it's connected to other things. I would keep looking, because this OH is not one unit. There's a bond in between there, so you'd have to keep going. But yeah. Okay, so we've labeled our first one. We discovered it was R. Okay, now I'm going to delete a little bit here so I can focus on my. my blue carbon here. So immediately I notice we have 2 oxygens. Okay, and by the way, we assume that there is a hydrogen here in the back. Okay. So immediately, like I said, we have 2 oxygens which have to compete for first and second priority, and we have to find out which one would win. Okay. So immediately we know our hydrogen here is going to be 4th priority, and our carbon here is going to be 3rd priority, because it's not highest atomic number like oxygen. Now we have to branch out. Okay. So we'll start with the oxygen on top. We're going to branch out 1. Okay, here we're going to branch out 1. We reach the same conclusion. We reach a carbon here and a carbon here. Now we have to branch out again. Okay, I'll branch out this way and this way. Okay, here I reach 2 carbons, while in the bottom, I also reach 2 carbons. Okay, now I need to branch out again. All right, so here I branch out this way and this way. I reach 1, 2, 3, 4 carbons. When I branch out down below, I reach an oxygen and a carbon. Okay, which one will win? Okay, 4 carbons versus 1 oxygen and a carbon, right? The oxygen, because this is not a battle of weight or electron. Battle of weight or electron, or not electron, I mean atomic mass. Can you go back 1 step? So I can just repeat what I was saying. Okay, so the first thing I determined was, I know for sure there's a hydrogen in the back that is 4th priority, and my carbon here has to be 3rd priority, because it has no chance at competing between 2 oxygens which have a higher atomic number. So therefore, I need to branch out from the oxygens because they're the same atom. When I branch out once, I get 1 carbon there and 1 carbon there. Okay. And so I'm stuck again. Okay, I need to branch out 1 more time. 1 this way and 1 this way. And then when I branch out the same amount, just one branch more on the bottom carbon, I get carbon there and a carbon here. All right. And so that doesn't help me because that means I've reached, sorry, that should be erased. That means I've reached 2 carbons on the top and 2 carbons below. We're still stuck again. We need to go a step further. All right. On the top oxygen branch that I've been creating, I reach a carbon here, a carbon here, a carbon here, and a carbon here. All right. So 4 carbons on the top. On the bottom, I reach an oxygen and a carbon. And like Yusuf said, we are going to prioritize the bottom, even though we have all of these carbons we just found. Let me highlight them. This one, this one, this one, this one. We found an oxygen, which is much higher priority than a carbon. So we're going to go with the bottom pathway as our highest priority. Okay, this will be number 1. All right, and then this will be number 2. Okay, so we're going to connect everything. 1, 2, and 3. This will give us clockwise, going in the right fashion, so R. Exactly, Nathan. Yes, even I, when I was like first learning this, I totally thought it was based on like the total atomic number, like the total mass, like the total amount of atoms. But that's only when you reach a dead end, basically. So I can show you an example of that. But it's more about whichever has the highest atomic number, not the total greatest, combined. So it's not a sum game. It's a race to highest priority. Okay. However, if there was no oxygen here, so let me erase that. If there was no oxygen here, there was, let's say, okay, a methyl group. Okay, and therefore, once we've reached that branch, then we see that there's only 2 carbons versus 4. In that case, we would go and prioritize this oxygen. Okay, in that case, we would prioritize this oxygen because we've already reached a difference, and that difference is there's 4 here of the same thing versus 2 here of the same thing. And we'll also kind of see that happen with double bonds, where if you see, if you have something like, like this, the one right here would be higher priority because it's as if you're connected to 2 oxygens as opposed to 1 right here. Okay, so then this one would have higher priority than the other, and yeah, so it's only a sum game at the end of the line, basically, when you've reached no other difference except for the number of atoms. Okay. So what I was saying, let me erase this. All right, so we established that we need to go 1, 2, 3, and we found we have R here. And we don't need to, sorry, 1 second. We don't need to flip anything because our lowest priority group is in the back where it should be, okay? So then we will get R as our answer for this as well. All right, so let me answer some questions. If they don't draw out the hydrogen, yes, we do assume, for example, if you're given something that looks like this, then you assume there's a dashed hydrogen in the back, okay? But if you're given something like this, then you assume there's a wedged hydrogen, okay? So for every stereocenter, there will be something that's wedged, there will be something that's dashed, okay? You're not gonna see 2 dashed things or two wedged things. It doesn't really make sense in 3D space. So yes. Okay, any more questions? And then I'm gonna jump to my last example. What if there's already a wedge and dashed, but you need to add a hydrogen? You're not really going to see that because that doesn't really make too much sense to draw. You're saying it would look something like um, that, and then you have to like draw the hydrogen, which is possible, and then you'd need to move this back, move to back. Can you go over how to flip them? Simply, if you end up having, for example, in our example we were just looking at here, the hydrogen here was in the back, but if it was in the front, so if this oxygen was wedged or dashed, sorry, and then our hydrogen was wedged, all we would need to do at the end, notice how we got an R, all we need to do is turn it into an S, that's all. So convert whatever we started with after we just do the problem like normal, we got an R, we turn it into an S, okay? So that's all we need to do. Like I wrote right here. Yes, it is that easy, yes. And it'll be right every time that way. Okay, so last example here. I'm going to draw in my hydrogen, which I assume is there. Yes, and no, I'm not kidding at all, please. That is the way to do it. Hopefully it saves you time. Okay, so our nitrogen here would be our first priority, right? Because all we have to compare it to is hydrogens and carbon, or carbons and hydrogen. And so we know our hydrogen here would be fourth priority. So it's a head-to-head battle between, yes, so if the hydrogen is wedged, you flip it so you can put it in the back. But if it's in the back, keep it how it is, it's all good. And don't change your answer. So, okay, so now we need to see which of these carbons should be prioritized. And it's not too bad. All we need to do is branch out one step right here. Okay, so if we branch out here, we get a carbon, but if we branch out here, we get that oxygen, right? So this is going to be second priority, and this is going to be third priority. Okay, and we just need to connect our numbers 1, 2, 3 to get sorry, I'm really slow right now, to get S, okay? And we don't need to flip it to R because our hydrogen here is in the back, all right? So this is our final answer. You should get RRS, okay? You don't really need to know chair structures except for what equatorial is, what axial is, what is higher energy, equatorial versus axial, okay? And so equatorial is when the substituents are laid on, are crooked or like slanted and out on the sides, and those are low energy, as opposed to axial, which is straight up and down, and that's high energy. Eclipsed, staggered, yes. So eclipsed is like this. So this is staggered, okay? This is staggered. Eclipsed would look like this. Okay, that means the substituents are overlapping each other. Okay, that is high energy. This is lower energy because things are more spread out. Whenever things are getting close to each other, it's high energy. Whenever things are overlapping and touching each other, they are high energy because they don't want to do that. Everything wants to be spread out in space. Equatorial is low energy because they're spread out in space, okay? Axial is high energy. And that's because, yes, electrons are getting too close to each other and they're not comfortable with it, exactly. Okay. Any more questions about RNS? Actually, I do have a review that does cover more RNS, and I cover it pretty well. I would say I've hit all the good I'll hit all the good points. So more examples on my review for quiz 6. But again, this will also be recorded and posted. But yeah, So if we're ready, we can talk about the last two slides. So yes, I did say equatorial is low energy because things are more spread out, okay? Spread out in space. And yeah, so now we can talk a little bit about SN2, SN1, if we're ready. Can you go back, E, for equatorial versus axial? So I can re-explain, but I didn't write it anywhere. Staggered is lower energy because things are not overlapping. Eclipsed is higher energy because we have that overlapping, okay? Just think in general, whenever things are touching and close and overlapping, they are high energy because things want to be spread out. When things are relaxed and spread out, they are low energy. That's how they want to be in space. Okay, so SN1, SN2, you guys, wow. This was really confusing for me when I first learned it. And if you're taking Orgo next year, bless you guys, because this is your your second exam just on SN1, SN2. Also, all this stuff that Dr. Ray has put in for Orgo review is so helpful for Orgo. The first and second exam will help you a lot. So yeah, we can break this down. It's not that bad, and I hopefully with my organization here, you see all the information you need to know to answer any kind of question. Okay. So let's first talk about carbocations and degrees of carbons. So for carbocations, or for any carbon, we can label if they're primary, tertiary, or whatever. So in this case here, we have a methyl group actually. So this is kind of like zero order. Then we're going to hit first order. So, or not first order, what am I saying? This is primary. Then we have secondary, then tertiary carbon, okay, or carbocation. Just to clarify, if you see something that looks like this, okay, what kind of carbon is in there? What kind of carbon is that? Is it tertiary? Secondary, okay? So we do not consider the Cl or the bromine because they're going to be the leaving group, okay? We care about what this looks like after the leaving group has left, okay? So we care about this, all right? This is secondary. Okay. So yeah, in order of stability, when we can secondary go through SN1, SN2? Yes, absolutely. And in Orgo, you're going to learn the specifics of when it prefers to go one way or the other. Leaving groups are halogens, yes. Okay, so I'm going to explain why a tertiary carbocation is much more stable than something like a methyl or a primary carbocation, which is practically impossible in nature. So a methyl group is practically, it makes me like concerned looking at it because that is so unstable. It's probably like never, ever, almost ever going to exist. But over here, this carbocation is stabilized, okay? It's stabilized by the other parts of the molecule kind of sharing charges and and taking care of that carbon that has a positive charge, which is really uncomfortable with that charge. And so it needs the support of other parts of the molecule. Hydrogens, however, don't really provide that support. So that's why they don't provide stability. They don't do anything. And we find stability. We find stability going this way, okay? So carbocations are only found in SN1, all right? And we'll kind of break down the differences between SN1 and SN2. But just as a reminder, carbocations are only involved in SN1 reactions, okay? That's also what affects what kind of carbon, what kind of electrophile it attacks, or what kind of electrophile goes under SN2 or SN1. just to clarify here, so SN2 will always undergo usually primary electrophiles or primary carbons, while SN1 prefers tertiary. Like I just explained, it prefers tertiary because of that carbocation formation. Okay. On the opposite side, SN2 prefers primary. There's no carbocation formed for SN2. Instead, what happens, and I'll show you guys an amazing video. If you're in my Tuesday section, you guys already saw it. Basically, what happens is this SN2 reaction requires an electrophile. I'll draw an electrophile. So we'll have chlorine. Okay, notice this is primary, all right? And so we have a nucleophile here. And it's going to attack from the backside because this chlorine is kind of, it kind of creates this like, it's electron cloud. It's blocking a lot. So the nucleophile here is going to attack the electrophile in this position where the leaving group is. And the leaving group will leave simultaneously as it's being attacked from the back. And it needs to be unhindered, okay? It needs to be SN2 unhindered. It wants to be unhindered during the attack, okay? But SN1 needs it to be hindered. It needs it to be stabilized by that tertiary, by the other components of the molecule. So even though attacking it is not the most convenient when there's a lot of things coming out of it, the only way to form a carbocation realistically is by having that tertiary carbon. Okay, so it needs it. It needs let's say, I don't want to say hindrance, but it needs bulkiness. Like I don't know, it needs stuff or substituents. Okay, around carbon, unhindered carbon. All right. So let me have you guys watch the video really quick. 1 second. If you have Axelson, she showed us, if you're taking Orgo with Axelson, she showed us this video in lecture. Oh, sorry.
Primary halogenoalkanes undergo SN2 reactions, where the S denotes a substitution reaction. The N shows the reaction involves a nucleophile. 2 is the number of species involved in the slowest rate-determining step. A nucleophile is an electron pair donor. It is attracted towards species carrying a full or partial positive charge, with which it can form a dative covalent bond. Consider the reaction between a hydroxide ion in solution and bromoethane. Both reactants are involved in determining the rate of the reaction in a one-step process. The hydroxide ion attacks the carbon atom from the opposite side to the halogen atom, because the bromine atom, A, is so large it impedes the approach of the smaller hydroxide ion, and B, it repels the negative charge nucleophile. The lone electron pair on the nucleophile forms a new dative covalent bond with the partially charged carbon atom to give an unstable transition state complex. The complex behaves like an umbrella blowing inside out as the bonds rearrange into a tetrahedral structure. A bromide ion, called the leaving group, is released. Transition state complex. SN2.
Okay, we're going to talk about what just happened there. All right, so like the video is saying, this SN2 reaction happens in one step, okay? And I'll illuminate where that one step comes from. Over here, actually, I'll write this in terms of kinetics, okay? So if you remember steps in kinetics, like elementary steps, order, like in order in kinetics, in an SN2 reaction, we just have our electrophile coming together with our nucleophile, and they produce like the leaving group leaving and the products, okay? And this is one step, that's it, okay? So then the rates, this must be the rate determining step, right? So this means that the rate equals K with the concentration of the electrophile and the concentration of the nucleophile, because there's only one step involved. So this must be the rate determining step. Therefore, so we know there's only one step, and we know this is second order. So I'm going to put that here, one step and second order. The SN2, the 2 in SN2 stands for second order, okay? And again, here's an SN2 reaction I've just written out on the left. We see our nucleophile right here attacking the electrophilic carbon right there of the electrophile, and the leaving group leaves simultaneously within the same step. It leaves, okay? The leaving group leaves. So that is the mechanism which I just covered, and stereochemistry. So this molecule here, it actually doesn't really have stereochemistry because it's not stereocentered, but we'll just pretend it is. So let's see what the product would look like here. I'm going to rewrite this. I apologize. Okay, so we're going to have a product. So the leaving group has left. Okay, this nucleophile has attacked, and it's going to replace the spot that the leaving group was before. Okay, so I'm going to write exactly the same molecule except one thing. Actually, all right. So this is the electrophile. Okay, or sorry, the nucleophile. All right, now it's in the same spot where the chlorine used to be. But notice that it is dashed instead of wedged. I know that's stupid because it's not a stereocenter, but you're going to see this with like secondary carbons, an inversion of stereochemistry, okay? Inversion of stereochemistry, all right? On the opposite hand here, we have SN1 reactions, okay? So SN1 reactions are very different. They prefer, like I said, tertiary carbons because, or tertiary carbocations because of that carbocation formation. So we're going to see something like this. All right, so this is going to be our electrophile, and it's going to be attacked by nucleophile. Okay, and not yet though, sorry about that, not yet. This is for later. The first thing that's going to happen, so step 1, okay, is the bromine is going to leave by itself spontaneously, right? So not spontaneously in the term of delta G, so don't get that, sorry. It's just going to leave, okay? The leaving group is going to leave. This is actually very non-spontaneous. This is a very slow reaction because carbocation formations are very high energy. They do not want to happen. Carbons do not want a positive charge nor a negative charge. They don't want any charge. And so this happening is pretty high energy. And that's why having a tertiary makes it so much better than a primary, because being a primary carbon is so much worse when you form a positive charge. So now that the bromine has left, the leaving group has left, this is what we're left with. Okay, now this is ready for attack. Okay, I'm gonna bring my nucleophile here. And this time it has the ability to attack from the front or from the back, okay? From the front or from the back, okay? This allows a kind of stereochemistry, a mixed stereochemistry. So we're going to get R, we're going to get S, okay? The ratio of that, 50-50. By the way, okay, sorry, I was like, am I screen sharing or not? Oh God, I'm so sorry. I haven't checked the chat in like a whole 10 minutes. Axelson is great. You guys will enjoy it. Maybe not enjoy it. Orgo is pretty brutal, but she honestly like does the best to make a really difficult class doable. Can we have the link? Yeah, I can provide the link. I'll just put it in my playlist. Could you send the links to this video? Yes, I'll add it in my playlist. If I'm covering A and B today, I'm not sure what that's in reference to. What bonds are formed? I'm so sorry, you guys. I left you guys confused. So what bonds are formed and which are broken? Okay. So Jacob, I'm so sorry. What are you talking about, SN2 or SN1? Okay, for SN2, the bonds that are broken are the ones between chlorine and the carbon right here. So chlorine and the carbon. And the ones that are formed are between this oxygen and this carbon, okay? So, by the way, these arrows, a double arrow, oh, I'm not even showing you, oh, sorry. Okay. A double arrow means 2 electrons are moving. A single arrow like that means 1 electron is moving. This chlorine here, well, actually, this oxygen is kicking out this chlorine, and it's kicking out the chlorine and both of the electrons with it, okay? Well, this lone pair is coming in. So this entire portion here is leaving. This bond is being broken, it's leaving. What's coming in is this oxygen, along with the chain that it's a part of, and it's coming in here. Now it's attached, okay? Hopefully that's more clear. Okay, so this mechanism here is SN2, okay? SN1 deals with carbocations, not SN2. And is the one carbocation, maybe the primary cation, you mean, can it only attack from the back? So there's no situation that we've learned of where carbocations are only attacked from the back. In an SN1, so here, SN1, this is SN2. In an SN1, they're attacked from both the front and the back, both ways. Yeah, so Axelson, she's pretty good. Yes, she provides everything you need to succeed. It's an extremely difficult class, but if you do everything she has, everything, all the materials she gives you, all the resources, all the past exams she has available, just take advantage of it, basically. It's very possible to get an A. But you kind of have to sell your soul. That's what I had to do. Oh, yes. So don't worry about the hydrogen right here. Don't worry about the hydrogen. It has to go away because Okay, we'll clarify this. I'll just remove the hydrogen entirely. That's all good now. That's a nucleophile. And the OH group will be in the back in the product. Yes, it will be inversion of stereochemistry. So SN1 is 50-50 because it attacks from either the front or the back exactly. And that is also why they're both R and S configurations. Perfect. Does the nucleophile that attacks the alkyl halide always go away from you? From me? Do you mean from the halide group? So the chlorine wedge, it doesn't disappear. It's the chlorine entirely goes away. Okay, the chlorine entirely goes away. What gets replaced is the nucleophile in its spot. Okay, the thing that's wedged right here is the hydrogen. But yeah, so basically it not only takes the spot of the chlorine, but it takes the inverted spot, which is the back spot in this case. So I'm going to finish SN1 really quick because I have not finished that entirely, and you guys have a lot of questions. So let me cover that first. And also, I'm not a TA for Orgo 1, absolutely not. But you guys are in good hands. Honestly, I think you have to be a PhD student to be teaching Orgo 1. So okay. Before I continue answering questions, I need to finish SN1. So okay. So let's review what just happened. Step 1, leaving group leaves. Okay, leaves by itself. All right, and prefers obviously to have a tertiary, right? Tertiary carbon to be leaving from. That provides more stability for the carbocation, which we have right here. Okay, so now we have our carbocation formed, and the nucleophile is ready to attack. And I'm going to clarify here. I'm going to remove this hydrogen. I apologize. We're going to have a negative charge there. And our nucleophile is attacking, and it can attack from both sides. And so now we're going to see a mixture of R and S. Okay, so this is my nucleophile that's now connected to my molecule. And here's also another version of it, which equally exists. Already. So which one is R, which one's S? That's a little difficult because it's also not stereocenter, but I'll just add a random methyl there. And so that's 1, 2, 3, 1, 2, 3. This will be S and this will be R. All right, so this is 50% equal mixture. So racemization just refers to this mixture. Okay, racemization just means a mix of things. Okay, so let's answer some questions. Does the nucleophile that attacks the alkyl halide always go in the opposite conformation of the alkyl halide? So I'm not sure what you mean. Sorry, I don't know how to pronounce your name, Nithya, because we do see that 50-50 mixture of it hitting from the back and the front. Does the nucleophile that attacks the alkyl halide always go in the opposite conformation? of the alkyl halide originally in an SN2. Oh, okay. Yeah, so we always see that inversion of stereochemistry going on in SN2. So the formation of carbocats leads to racemization. Oh, yes. Can you fill out the table? Yes, I'm getting there. No worries. I can clarify the acid base breaking question I emailed about if you're covering that in this review. Oh, I see what you mean. Sorry. Okay, we can discuss it after the review. And can you clarify how you got S and R? I just did it quickly in my head, but basically, this will be first priority. This will be last priority. This side will be second priority, and this will be third priority. The one over here will be second priority because it has 2 carbons as opposed to 1 carbon coming off branching from it. And so I connect the 2, and then you get S that way. And then you'll get the opposite for the other. When the nucleophile attacks, you make it wedged or dashed based on the opposite of what was already there. Yes, for SN2. Okay, I'm going to jump back so we can finish what's going on here. So for SN1, remember how we had 2 steps? Sorry. Remember how we had 2 steps? That step 1 was that carbocation formation. Step 2 was the nucleophilic attack. That's going to be reflected in the elementary steps. So I'll write out the elementary steps here. So we start out with an electrophile, and that breaks up into the leaving group plus, let's say, the carbocation. Okay, and then that carbocation gets attacked by the nucleophile, and that gets turned into the product. Okay, and so there's 2 steps here, 1 and 2. These are the elementary steps, all right? So we know there are 2 steps, but the order is important. So this first one is the slow step, okay? How do I know that? Well, you should know that the carbocation formation is very slow. It's very difficult, like I was saying before, and so it only has one. So this is the RDS here. It only has 1 reactant. So the rate law must look like this. Okay, so it's going to be first order. All right, so we talked about the mechanism. We also talked about the stereochemistry. We see an inversion here. Okay, and on the right side for SN1, we see stereochemistry. We see a 50-50 mix. Okay. All right, and racemization just means that mix. So yes, we have it here, and no here. All right, so so I just did the RNS here, just like usual. So hopefully nothing new there. But let me know if you still have concerns, Jeff. Okay. So any more questions about SN1, SN2? Oh, by the way, I added, I'm so sorry. This right here, I added because otherwise I couldn't do the RNS. And so I'm just adding that everywhere here. Can you go over the mechanism? Okay, so would you like me to go over the mechanism for SN1? Because it's kind of what I was referring to with, so the leaving group leaves and then the nucleophile attacks from both sides right here. What does the check mean for mechanism? The check means that I went over it, that's all. The check means that I just covered it for both of them. How much should we know about molecular orbital theory? Well, I'm about to cover that in the next slide. Okay, so any more questions? Again, you're going to have everything. So if you don't get anything here, no worries, no panic. You will have all the slides available in case you miss something. So All right, so we're going to be, so SN2 attacks from the back, yes. SN1 attacks from the front and back, yes. What does inversion mean? Inversion means that if we start with something wedged, like over here, we are going to get something dashed over here. So we're going to go from R to S, or S to R. For SN1, sorry. For SN1, the rate law only includes the alkyl halide. Yes, absolutely. Because the rate determining step is the step in which the leaving group leaves, okay? So, by the way, in alkyl halide, which I know can be confusing terminology if you've never heard it before. So in alkyl halide, okay, just refers to a carbon or a group, whatever, with a chlorine or bromine or just any halide connected to it. So alkyl means carbon, and halide means means like a halogen or halide connected to it. Okay. Another common thing you should know: hydroxyl. I can't even spell. Hydroxyl means like an OH group. Okay, that's all it means. So those are some things to keep in mind. Can I go to the slide where I draw the mechanisms? Yes, I can hover over here. So unhindered carbon means it doesn't have a lot of substituents coming off of it. For example, a primary carbon is only connected to one other carbon or one other thing, and so it's pretty open. Okay, it's pretty unhindered. Okay, as opposed to a tertiary carbon, which is very blocked by other groups coming off of it, right? And so that'd be very hindered. Exactly, Jeff. Yes. Okay, so are we ready to go on to molecular orbital theory? Or do you guys have any more questions? Okay. How do I determine products? Like I was highlighting over here on the left for SN2, we start with a primary alkyl halide. And once that gets attacked, whatever the stereochemistry here was wedged, becomes dashed. And then the nucleophile takes up the spot of the halide or the halogen, okay? For SN1, we're going to start with a tertiary alkyl halide. That leaving group is going to leave. It's going to look something like this, okay? And then our nucleophile is going to attack, all right? And it's going to take the spots either wedged or either dashed where the leaving group used to be, okay? So hopefully that makes sense. I feel like having one lecture on molecular theory was not much, so I hope we aren't too, yeah. So you might be asked something like, what is the bond order or whatever it's called? So nothing crazy. Okay. So one eternity later, right? Okay. Now we can talk a little bit about molecular orbital theory, and we're pretty much done. So here you kind of have to memorize, unfortunately, the kind of orbital orders. So we're going to have bonding and anti-bonding. Anti-bonding are the ones with stars, okay? And so that's what we're going to see here. So if I choose a molecule, let's say something like this, okay? First thing you need to do is ask yourself, how many valence electrons are there, okay? In regular O2, there's going to be 12, okay? In O2 2 plus, there's going to be 10 electrons, okay? And so let's choose this one for our example. Yes, so bonding is simply all of the orbitals here that are not starred, okay? Anti-bonding are the orbitals that are starred. That's simply it. So I have 10 electrons that I need to fill up here. Okay, so I'm going to go ahead and do that. So far I've hit 6, 7, 8, 9, 10. Okay, so one thing I notice is these are not alone. Okay, so for example, if we had it up to here, they would be alone. But there's no, these are both complete lone pairs. And so this is going to be diamagnetic. Okay, so this is not reacting or not interacting, let's say, with magnets. Okay, but if they were like this, they would be paramagnetic and interact with magnets. What else? So we can also write what the LUMO and HOMO is. So the LUMO is the lowest unoccupied orbitals. Those would be these. Okay, these would be the LUMOs. The highest occupied would simply be these orbitals right here. Okay. And if we wanted to find out what the bond order was, we would count how many are bonding, how many are anti-bonding. Here we have 1, 2, 3, 4, 5, 6, 7, 8 bonding, and we have 1, 2, just 2 anti-bonding. Okay, we're going to divide that by 2, and we should get 3 as our answer. Okay,